let's do another example. This time let's kick up the dimension by 1 to 3 by 3 example. Okay. So here we are going to examine the following system. And now this time I've just because I feel like it, I'm going to call my dependent variables x, y, and z for no good particular reason. Okay. So in this case, I'm going to have three equations in three dependent variables x, y, and z. This is a homogeneous system. So we're going to have x prime, y prime, and z prime. I just feel like it. Okay, I don't want to keep writing subscripts everywhere. And here's what my what the equations will be. It'll be x plus 3z. It'll be negative x plus z. And z prime will be 2x plus 2z. Okay. And you notice, okay, there's no y's involved. And yeah, right. Good job. You noticed. Okay, now let's rewrite this in matrix notation. We get x prime, which is going to be x, y, z. Oh, is that fair? Oh, this could be very confusing, I realize. X, maybe I'll define x. X is going to be x, y, z. Okay, this is the kind of, yeah, this is the kind of thing you just have to get used to. Just deal with it, all right? Yeah, okay. So then x prime is going to be x prime, y prime, z prime, and our system becomes, in matrix representation, x prime equals, now I'm going to write down the 3 by 3 matrix corresponding to this system. The order of my variables is going to be x, y, z. So I got to respect that when I write down my system, all right? I'm looking now at the coefficients in this first matrix, equation rather, excuse me. The coefficients in this first equation. And I get 1, 0, 3. Why 0? Because there's an invisible 0y that nobody bothers writing, right? Oi. So I get 1, 0, 3 for my first row. For my second row, can you guess? I get negative 1, 0, 1. And for my third row, I'm going to have 2, 0, 2. That's my P. This is what's playing the role of P here. Okay? And then finally we have X. Okay. This is my system written in matrix notation. Okay? And of course, what I need to do is find the eigenvectors of P and associated eigenvalues. Okay? So we're going to write down the characteristic polynomial. The characteristic polynomial of P is the determinant of P minus lambda I. In this case, I is the 3 by 3 I. But, I mean, all that you need to do here is take the determinant of what you get by putting minus lambdas down the diagonal. So this is the determinant of the 3 by 3 matrix. 1 minus lambda, 0, 3, negative 1. Now, 0 minus lambda, which nobody bothers writing the 0, we just write minus lambda, yes, 1. And then 2, 0, 2 minus lambda. Okay. Going to compute the determinant of this, and it looks a little scary, except that you see, I hope, that column 2 has lots of zeros. Very nice. Do you see that? Column 2 has lots of zeros. So let's cofactor expand along column 2. Notice that this non-zero entry in column 2, negative lambda, is sitting at the 2, 2 position. 2, 2. Second row, second column. 2, 2. And so we're going to put a negative 1 to the 2 plus 2 as the sign. I know you know. Negative 1 to the 4th power is 1. So that's really just 1. But I'm putting it there just to remind you of how cofactor expansion works. Then we put the entry itself, which is negative lambda. And then we multiply this by the determinant of the 2 by 2 that we obtain by deleting the second row and second column. That's a 2 by 2, 1 minus lambda, 3, 2, 2 minus lambda. It's very easy to get mixed up in this, so it's really important to be organized. And God, I hope I didn't mess this up. I think we're okay. I think we're okay. Negative 1 to the 2 plus 2, as I said, is 1. So this is 1. Oh, and I'm not going to bother to write 1. Negative lambda we have out here. And then we're going to multiply that negative lambda by 1 minus lambda times 2 minus lambda. That's the product of the diagonal entries minus the product of the off-diagonal entries. Minus 6. Now I'm going to work with what's inside the parentheses here to expand that into a quadratic in lambda. So I get negative lambda times, now I'm going to expand this out because I eventually want to find the roots. Hopefully this thing factors. We'll see. I get 2 minus, let's see, minus lambda minus 2 lambda, so that's minus 3 lambda plus lambda squared minus 6, yeah? And this becomes, with a little bit more work, negative lambda times, now I'm going to write it in the opposite order because my brain likes looking at it like that. Lambda squared minus 3 lambda minus 4, I think. Is that good? I think that factors. I think this factors into lambda minus 4 times lambda plus 1. Yeah, I did it. Very proud of me. Now, do you notice that I never bothered to distribute this negative lambda out here? Sorry, oh, I did that badly. Let me just pretend that nuclear... It looks like I never distributed the negative lambda. Okay? And the reason is because I like having that negative lambda out there. This is partially factoring my cubic for me, right? So it's a little bit counterproductive for me to fold it back in. It like makes the mixture more complicated, not less complicated. We want to separate the oil and water. We don't want it all mixed up. I don't know if that made any sense, but you're just going to have to deal with it. In any case, what we learn from all of this are what the eigenvalues of P are. From here, we learn that the eigenvalues of P are lambda equals, now we just read off the roots. In this case, there is 0, 4, and negative 1. What? An eigenvalue of 0? Is that okay? Is that allowed? Yes, it's allowed. Okay, it's allowed. And we're going to treat it exactly in the same way that we would treat any other eigenvalue. Okay? And indeed, that's what we're going to do next is try to figure out eigenvectors associated with each of these eigenvalues. Okay? Let's start with negative 1. I don't know why. There's no do I care? No, I don't care. It doesn't matter what order you do it in. So let's just do lambda equals negative 1 first. So I want to solve the system P minus negative lambda I. So sorry, P minus lambda I, which is P minus negative 1 times I. So that's P plus I times V equal to 0. And I want to solve for non-zero V. So I'm looking, basically, I don't know why I bother writing this. I'm looking here. And what I'm going to do is replace lambda by negative 1. And write down the augmented matrix that I get. So if I do that, I get the matrix. So let's see. I get the matrix 2, 0, 3. Then negative 1, 1, 1, and 2, 0, 3. Okay. All right. Oh, and I gotta augment this matrix with the 0 vector. 0. I don't gotta, but I'm gonna. Okay. Now, we could row reduce this, yes? That might make things a little bit simpler to understand. First thing I notice, and I hope this is screaming at you as well, is that row 2 and row 3 are identical here. So I can kill row 3 by adding -1 row 1 to row 3. So I get 2, 0, 3, 0, -1, 1, 1, 0, and then just a row of zeros, which is good news. I'm going to further simplify my life by adding an appropriate multiple of row 1 to row 2. Or what? Okay, maybe one thing I could do is just make this thing here equal to 1. Sometimes this is recommended by linear algebra textbooks. So I'll go ahead and do that. I'll multiply row 1 by 1/2. So I get 1, 0, 3 halves, 0, -1, 1, 1, 0, and then 0, 0, 0, 0. Okay? Don't ever say I never did anything for you, because this is pain. No, let me not say that out loud. So now what I'm going to do is add row 1 to row 2. 1, 0, 3 halves, 0. Add row 1 to row 2. So that's going to kill the -1, 0, and then leave that alone. This becomes 5 halves. Ew. And then 0. And then we have a row of zeros. Okay. Okay, now I'm going to interpret this. Okay? If I think of my eigenvector, or my proposed eigenvector as having entries v1, v2, and v3, then this first equation tells me that v1 plus 3 halves v2, or no, I'm sorry, 3 halves v3 is equal to 0. And this second equation is telling me that v2 plus 5 halves v3 is equal to 0. So we can see that in each of these equations, I can solve for v1 and v2, respectively, for v3. Does that make sense? You can't answer. So what we learned is that v1 is equal to -3 halves v3, and v2 is equal to -5 halves v3. Okay? So when I go to write v, which is, of course, v1, v2, v3, I could rewrite that totally in terms of v3. I could rewrite this as -3 halves v3, -5 halves v3, and then v3. And v3 is free to be whatever it wants to be, you see? I can choose anything. Well, I can't choose 0, because if I choose 0, then v is going to be the 0 vector. 0 vector is never an eigenvector. Never. For very good reasons. Okay? But in this case, I'm going to choose v3, I think, to be -2. Why? Because there are two things that I hate. I don't love. Fractions, I don't love. And negative signs, I don't love. And I feel like I minimize negative signs and fractions by choosing v3 to be -2. Do you see what I'm saying? So let v3 equal -2. And what we obtain is that v is equal to 3, 5, -2. And that's my eigenvector with eigenvalue lambda. I'll just denote that like this. Equals -1. Okay. All right. What I would like you to do now is pause the video. I mean, you should be doing this kind of thing anyway. Pausing the video, trying to compute. Let's do lambda equal to 4 next. Find an eigenvector with eigenvalue 4. Okay? I'm going to pause the video, and I'm going to do the work. And then I'll unpause the video, and you'll see a bunch of work appear on your screen. But you should pause your video, and you should get out a piece of paper. If you're not taking notes, what are you doing? Okay, you should write in your notes and try to compute the eigenvector associated with eigenvalue 4. Okay, I'll see you in a little bit. It's gonna feel instant on the video because I'm just gonna pause it and then re-record. Okay, see you soon. Okay, I did the work. This is what I ended up getting. Is that what you ended up getting? You might have gotten something different, of course. There are lots of eigenvectors with eigenvalue 4. In fact, any scalar multiple, non-zero scalar multiple of this will also be an eigenvector. So for example, if you put down pi, 0, pi, that would also be an answer. Or negative 8,000, 0, negative 8,000. That would also be an answer, okay? Doesn't matter. They're all good, but this is the one I came up with. Let me walk you through how I did it. So lambda's 4 here. So I know what I'm going to be doing is plugging in 4 into this matrix here for lambda. Yeah. And so if I do that, I think I did it right. I get this matrix here. And this is not optional. You should get the same thing. Okay. Then I did row reduction. Okay. In order to understand this linear system in V1, V2, and V3 a little bit easier. What I did is I multiplied the first row by negative 1/3 to make this 1 right here. And then I can see with my eyeballs that row 1 is a scalar multiple of row 3. You see that, right? So I can kill row 3 by adding an appropriate multiple of row 1 to row 3. I don't know. I'm not even indulging in what multiple it is. I don't care. If I can detect with my eyeballs that row 3 is a scalar multiple of row 1, I know it can die under row reduction. So I'm going to kill it. Okay? So then I got this matrix. Notice row 2 didn't change. Now I want to kill that negative 1 right there. Okay? So I add row 1 to row 2. Okay? Now in linear algebra class, there's something called reduced row echelon form, where they're going to further recommend that you make that negative 4 into a 1, etc. I don't care about that, okay? What I care about is what this is informing me, how this is informing me about the eigenvector. What it's telling me is that negative 4 V2 is 0, and that forces V2, of course, to be 0. It must be 0. When I say it, V2 must be 0. That's why I got a 0 here. The other constraint is that V1 minus V3 must be 0. What that's saying is that V1 must be equal to V3. Hence, I chose V1 to be 1, and that forces my hand in V3. It must also be 1. So this V here is an eigenvector. Yes? Cool? Great? Okay. Let's play this game one more time. Now we're going to take the last eigenvalue. I don't know why I went in reverse order. We're going to take now lambda equal to 0. Okay? So I want you to pause the video, compute an eigenvector with eigenvalue 0. An eigenvector of what, you ask? An eigenvector of P. This P right here. How? You're going to plug in lambda equal to 0 into here and solve the system. This thing times V equals 0. Okay? Go. Pause. Okay, here's what I got. Did you get this? Or some scalar multiple of this? If so, great. Let's talk about it. So, of course, what I did is I put lambda equals 0 into this matrix right here, and ended up with this matrix down here, which I've then further augmented with the 0 vector. Okay? You can hopefully check that arithmetic is correct. Then I did row reduction. Okay. What I did is I added row 1 to row 2. That gave me 0, 0, 4, 0. And then I added negative 2 row 1 to row 3. That gave me 0, 0, negative 4, 0. And you can see, row 3 is a scalar multiple of row 1. Row 2, I mean. So I can kill row 3. Furthermore, I'm going to do two moves at once. I can make this 4 into a 1, but just by multiplying row 2 by 1/4. So that's what I did. I did those two moves, and that's the result. And now I'm going to kill this 3 because I feel like it. Because I can add negative 3 row 2 to row 1. Negative 3 row 2 to row 1. And that kills that 3 there. And what I end up with is this very sparse matrix, tons of zeros. We like it. Okay? Okay, now interpret these rows as equations. We get V1 is 0, must be 0, and V3 must be 0. Do you notice? No condition at all on V2. That means V2 is allowed to be whatever it wants to be. Anything. As long, and we can make, in particular, a non-zero vector by making that V2 be something non-zero. So that's what I've done. I made a V2 equal to 1. Okay. Great. So now I've got my 3 eigenvectors. You see them? Here's one, there's another, and there's the third. Now I'm going to take those 3 eigenvectors, and I'm going to make solutions out of them. These solutions I believe I'm going to call x1, x2, and x3. Okay? So x1 is going to be the eigenvector, it's going to correspond to the red eigenpair that I've computed. Oh, maybe I should do this in green just to make the colors look good. So x1 is going to be, so remember, our ansatz is VE to the lambda t. So that's going to be 3, 5, negative 2 times e to the lambda, which is negative 1. So that's negative t. Okay. x2 is going to be, I'm looking now at my purple eigenvector. So I have 1, 0, 1 times e to the lambda t, that's e to the 4t. And finally, my x sub 3 is going to be 0, 1, 0 times e to the 0t, which is interesting. E to the 0t, I mean, it's kind of interesting. E to the 0t is e to the 0. Anything to the 0 is 1. Okay? So this is the solution. It's a constant vector. Okay, cool. So what this is saying, sorry. We notice we have 3 distinct eigenvectors. Eigenvalues in this case. They're all real. So we know that these 3 solutions, this one, and this one, are linearly independent. Okay? And so I can form the general solution to this system of differential equations by mashing them together into a superposition. Huh? So I learned that my general solution is x equals c1 x1. Well, I'm not even going to bother writing. I'm just going to write 3, 5, 2. Oh my gosh, why? Negative 2. Times e to the negative t plus c2 1, 0, 1 e to the 4t plus x3. Sorry, c3 0, 1, 0. That's my general solution. Okay. Now I want to do one more short video where we take this system and we incorporate an initial condition and then solve. Okay? All right. See you in the next one.